This series is a journey to the most exciting frontier of science, the brain. Every day we're learning more of how this miraculous organ works. Last month was our introduction. We showed you the anatomy of the brain and the frontiers where brain science was taking us. Tonight we look at one of the most instructive areas, visual perception. 1/4 of our brain activity is about visual perception, so the brain is devoting about 25% of its power to vision. Think about it. What the visual system tells us is at the core of our impressions of the world. What is real and what is beautiful, what is permanent and what is changing. Vision is one of our 5 special senses, including hearing, smell, touch, and taste. We focus on vision because so much of our world is visual. Also, we understand more about vision than the other senses. Most of us think that what we see is only determined by our eyes, but that is only the beginning. The extraordinary happens in the brain as it takes the inverted image from the retina and passes it to the cortex, where the brain creates a perception of the seen world. It is in the brain where seeing happens. Patterns of light and color are translated into objects and events, things that are meaningful for us and our survival. So the question is, how does the brain produce our perception of what the eye has captured? That's the difficult and the exciting part. How does this computation work? How does the brain organize the patterns of neural information into the visual perception we have? How does it make inferences about the world around us? What clues does it use? And how does it compensate for changes in our visual environment? What assumptions does it make? How much of its activity is passive and inferential, and how much of it is the active collection of information? We know from the study of the development of that visual experience in the very first years of life, when neurons and their connections are being forged, is crucial for normal vision. We're also learning what happens if during these early years one is deprived of visual experience. There is now encouraging news that the visual system is surprisingly plastic and able to recover from injury and to learn anew. We will ask what we know about blindness in various forms, and we will learn more of the relationship between vision and other sensory processes. So we looked at the introduction in our first episode. Tonight you've chosen visual perception. Why do we start there?
We chose this together, Charlie. We chose it because we understand the visual system better than any other system of the brain, and because it is a model for how the brain works. If we understand how vision works in the brain, we have a very good understanding of how the other sensory systems work.
You have suggested sort of 4 ways that we ought to look at this, 4 themes. The eye is not a camera. Sensory functions are localized. Visual computations are hierarchical. And plasticity in the brain is pervasive and crucial. Take me quickly and summarize what we mean by the eye is not a camera.
You've made some of these points. The eye takes incomplete information from the external world. It is not absolutely faithful to the external reality. It takes things that are important, it throws other things away, it emphasizes certain parts of the image, discards others. The brain is the creative organ that makes sense out of this, that gives you a feeling of 3-dimensional space, of faces looking at you, at landscapes. That is completely a reconstruction done by the brain. The brain does this in an orderly fashion. Each sensory system, the visual system is a perfect example, has a specific spot in the brain. So there are a series of relays that are localized in everybody's brain in exactly the same way. And the visual system has its own space, the touch system has its own brain space, the smell system has its own space. Every sensory system has its specific location. And it is organized in a hierarchical fashion. There are a series of relays that operate on the information in progressively more complex fashions. So we'll see the early relays, the retina and in the thalamus, see whether or not light is present or absent. They respond to small spots of light. As we get onto the cortex, the cells in the cortex begin to respond to edges, to bars, whether they're horizontal or vertical. Later on, we get to more complex images, and ultimately, as we'll hear from Nancy Kanswisher, we'll actually see how the brain responds selectively to faces or to landscapes. So this is a progressive processing operation that the visual system performs.
And tell me about illusions.
The brain makes guesses. As a result, it can be deceived. And we can sometimes present it with a two-dimensional form that it sees as a three-dimensional form and vice versa. And one can actually see the creativity of the brain at work. Because in solving an illusion, figuring out that there is a dog here, or there's a face here, there's almost an aha experience, like a sense of creativity. And in a very primitive sense, we see in the visual system of everyone, you, me, and the person on the street, the creative process that probably is specialized in genuinely creative people that do great science, that do great art. So we see in the visual systems the elementary forms of this creative process. It's built into the brain.
Let's begin by looking at the anatomy. Our anatomical expert is with us again. Welcome back.
My job is to tell you where things are.
Exactly right.
So,
all right. So we have pictures.
We have pictures, and having started with the idea that the eye is not a camera and that that's not how the visual system works, we will start by showing you that the eye, in fact, does form images like a camera does. And so this is a cross-section of the eye taken as if through this plane. In other words, if somebody had taken my eye and divided it in half along the midline of my face. The front of the eye is here. And what you see is an image being formed of a point in the world. The light rays are focused just as a camera or any other optical system focuses the rays onto the light-sensitive part of the eye, the retina, which lines the whole back of the eyeball. The optical apparatus at the front of the eye works like other optics we understand. So there is a cornea, which provides most of the power for forming the image, and the lens, which is the adjustable part of the system that lets us focus on near and far objects. Now, what we're mostly concerned about here, though, is what happens once the information reaches the retina and forms an image on the retina. And at that point, the photoreceptive cells that line the back of the eye collect the information from the image and funnel it through this single, rather narrow channel, the optic nerve. Now, the eye is doing something very dramatic right away in terms of neural function and neural circuitry. The retina is a part of the brain. The fact that it happens to live in the eye is a matter of anatomical convenience, but the retina contains the kind of circuits that we find in the central nervous system. And those circuits actually perform some very elaborate computations, most of which we're not going to be talking about in detail today. But one very striking thing that the retina does is something that we're all familiar with in terms of, for example, how a digital camera works or how a video camera works. We take a lot of information and we compress it down so that it will fit conveniently onto our tapes or onto our hard drives. The retina has about 100 million photoreceptor cells in it, which sense the intensity and color of the light at each point in the image. And the information from those 100 million receptors is compressed down so that it comes out of the eye along the optic nerve in about 1 million fibers. So there's about 100 to 1 compression of the information performed by this circuit in the eye, so that what transfers into the brain can be, I think arguably for physical reasons, carried along this optic nerve. One of the things about the eye that is very striking, and a striking aspect of its design, is that its visual resolution, its acuity, is only very good at the very center of gaze, exactly where you're looking. And you can become aware of this yourself if you look carefully at Eric Kandel's face, for example, as I am, and then try to work out the details of what color shirt Pawan Sinha on my left is wearing. You can't do it. And the reason is that your visual acuity falls off as you move away. And that's because your retina is very specialized for detail in the middle, and its sensitivity falls off to the periphery. And as a result, you have to move your eye around. So the way you make up your picture of the world is by moving your eye from place to place and capturing multiple snapshots and assembling them into a percept. Now, it has to be said that all of us here work on the central nervous system, and most of what we're going to talk about today has to do with what the central nervous system does. And so here, what we're doing is looking at a view of the brain from the back. This same brain that we have in the middle of the table as a sort of colorful representation is here rendered, and what you can see here is a cone of light rays, the light rays forming an image, entering the eye, which is visible in shadow on the left-hand side here. The optic nerve passes here, as you can see, into a relay nucleus in the core of the forebrain called the thalamus. This nucleus is called the lateral geniculate body, but it's a thalamic relay nucleus. The thalamus is a part of the core of the brain that actually connects specifically to all parts of the cerebral cortex, that sheet of cells that we've discussed before about that do most of the interesting computations the brain does. signals from the visual thalamus pass to the visual areas of the cerebral cortex, which are marked here, some of them, in different colored zones.
It also shows very beautifully, as Tony outlined, this is characteristic of other sensory systems. There's a hierarchy. There are a series of relays that process information in progressively more complex fashion. And that's why this is such an instructive system to study.
Well, I think this example is a good one. This is a famous old example of the principles of gestalt psychology, which are the principles by which we organize information. And when you first look at this picture, it's very hard to figure out what it is. In fact, it just looks like a bunch of light and dark splotches, and you may look at it for a while and just see light and dark splotches. And that actually is the information that your eye is getting from this picture, and your brain has to figure out what to do with it. Now I can show you what you should do with it, because we've here drawn some lines on top to show you that there's a dog there. It's a Dalmatian dog, and the Dalmatian dog has these light and dark spots on it. And if we go back to the original picture now.
Unbelievable.
Isn't that unbelievable?
Yes.
That's fantastic.
Now that you've seen what it really is, now you can hold that image together and you can see how to organize it. And now normally, in our normal vision, everything seems so automatic, we don't realize that this is really what's going on all the time. Our eye gives us this light and dark information, but it doesn't come in an organized form. And the problem is light and dark can come from many different sources. It could be a light or dark spot because the fur is got black or white pigment in it, or it could be some shadow that's being cast causing it to be light or dark, or it could be the edge of the dog where the dog stops and the background starts. So this information that you're given at the level of the eye is very ambiguous, and so there's a sort of a detective problem, a problem-solving task that the brain has to deal with, which is how do you piece all these bits of information, each piece being ambiguous, how do you piece it all together into a single coherent story that tells you about what's really in the world.
Let me turn to Nancy. Tell me about how you have begun to understand and focus on the localization of function.
Right. Well, our work builds on lots of prior work using behavioral measures, right? So we're interested in face perception, and one of the reasons we chose to work on face perception is that there were lots of reasons to think that the brain would have special machinery for processing faces. So if we show that movie, you'll see in a display that when a face stimulus is presented upside down, you can't tell what it is. And this is characteristic of faces in particular. You don't see it for other kinds of stimuli. It's perfectly easy to recognize a chair or a dog or a tree if you see it upside down, whereas face recognition is severely impaired when you see a face upside down. So that's been known for decades. And because of that work and other work like it, there was reason to think that the brain has special mechanisms that it uses when it recognizes faces. And so the idea was that at the higher level stages from where Tony's been talking about, at the higher stages of the visual system, there might be special machinery in there for face recognition. So we've looked at that with brain imaging methods, where you pop a subject in a scanner and show them faces, and you can see that part of the brain turn on in brain imaging methods when a subject looks at faces. So right now, my face area, which is right there in my brain, is active because I'm looking at your face, and now it's off, and now it's on, and now it's off. And I know that because I've scanned myself and hundreds of other people looking at faces
you can
and
tell
objects,
when it's on and off.
and you can just see it turn on and off.
The fact that face recognition has a localized function, is it because it's more difficult, more what?
That's a great question. I'd love to know which mental functions get their own private piece of real estate in the brain and which don't. So in my lab, we found a few. We found regions that are specialized for face recognition right here. I'll show you on the brain. I can show you where it is. That's the front of the brain. It's looking at you. And then if we turn it upside down, so you can see the bottom of the temporal lobe right here. So on me, that's right there. That face area is right about here in the brain. And we've also found other specialized regions. So we expected to find that face region because of the work that Eric just mentioned on people with brain damage. When they had damage in this general region, they tended to have this difficulty recognizing faces. So that wasn't too much of a surprise, although it's really fun to discover. But since then, we've found several other regions that we didn't expect in advance at all. So one is a region that responds when you look at places and landscapes. And it's right next door, a little further forward, right about there in the brain on both sides.
Okay, which goes to suggest that the programs for learning, the programs for acquiring vision, can be initiated even late in life.
You can also see this in certain brain areas. So each of us learns to read. And when you learn to read, there's a particular part of the same visual area of the brain that I was talking about before that comes to respond selectively to words and letters presented visually. And it's right in there. And it's very small, but you can find it in almost every subject. And since people have only been reading for a few thousand years, humanity hasn't been reading very long, that piece of brain cannot be the product of natural selection. So it must be that each of us in our lifespan wires up the circuits based on experience to make that region selectively responsive to the orthographies of the languages we know. A colleague of mine, Cheng He, has recently shown that region can develop even if you don't learn to read until well into adulthood. So he found, first of all, he found that region in Chinese subjects when they look at Chinese characters. That's sort of expected. But then he found a bunch of Chinese illiterates, and he scanned them, and he did not find that region. And then he taught them to read. And then he scanned them again. And there it was. And some of these people were 40 when they learned to read, and that region still developed. So some of these regions are extremely plastic and can develop late in life.
And usage makes them come alive, so to speak.
Yeah, that's right.
Yeah.
That's right.
But what should we take away? What do you want the people at home who see this to come away with?
I think the important thing to learn is how synthetic the brain is, how it lives in a world from which it extracts limited information, and how much of what we know about the world is reconstructed in our brain. And this not only holds true for vision, it holds true for all senses. We see the complete picture even though we get fragmentary information. So it makes us realize how magical the brain is.